Myself Sindhu Rekha, Assistant Professor from Department of ECE in Mlritm Engineering College. Today I am going to discuss about the test and testability subject. Before going to this subject, we should know the course outcomes of these subjects. So in this, acquire the knowledge of fundamental concepts in fault and fault diagnosis, and also learn the test pattern generation using linear feedback shift register and cellular automata, and also know the design for testability rules and techniques for combinational circuits, and knows the scan architecture introduction, and then make sequential circuits are testable. And these are the course outcomes of this subject. After completion of test and testability subject, student learn these many outcomes. And then coming to today's my lecture content, in that first one is testing introduction, types of testing and need for testability, and then controllability and observability, and last one is fault model. So coming to the introduction part, so what is testing and why you go for testing means, after fabrication of IC, not only IC but every product we need to test before releasing into the market. So then only we can provide the good product to the market. Okay, so that's why you need to test every product. So like that, after fabrication of IC, it must be verified. So that is called VLSI testing. So in VLSI testing, IC to verify its correctness, and also test results are satisfactory. If it is satisfactory, then only chip is qualified to be shipped to the market or to the customer. That is called VLSI testing. So and then CMOS IC test. So here CMOS means complementary metal oxide semiconductor. It is a combination of PMOS and NMOS. These are three types. One is functionality test and logic verification test, and second one is the silicon debug test, and third one is the manufacturing test, or also called as gate level testing. So in this functionality test, we can only verify the functionality of the circuit by using the software tools, and then we can do the simulation part. That is called functionality test. In silicon debug test, we can verify the debugs here. So this is very expensive test compared to the functionality test. And then manufacturing test is nothing but before releasing into the market. So every IC should be tested at the manufacturing level. So another name of manufacturing test is called gate level testing. So this is the introduction about the IC testing. And then testing is done at several stages. Those are wafer level, package level, board level, and system level, and field level. So wafer level is nothing but die is tested at wafer level. Here die is nothing but IC, integrated circuit. So at the IC wafer level, you can test the IC. And then package level, after separating the IC from the wafer, we can go for the package level testing. And then going to the board level testing, the chip is placed in board and board is tested. So after packaging is done, we can place the IC into the board. Then only we can test the IC. And then system level test, board is placed in the system and checked if system works as specified. That is called system level testing. And then field level, end user test the system while using a system. These are the testing stages. So these are the diagrammatic representation of wafer level testing, board level testing, and system level testing. So this is the wafer level testing. So here small particles are there. So every particle is called one IC. So here we can test the IC. After completion of this wafer level test, you can go for the board level and then placed into the system level. And then coming to the testability. So coming to the definition of testability, the ability to control the and observe the internal nodes of the circuit is testability. We can simply call as testability is nothing but controllability plus observability. So both the combination is called testability. So here controllability definition is the ability to apply inputs to circuit and test and place it in specified test, that is called controllability. And then observability, the ability to observe the states and outputs, that is called observability. Controllability is nothing but we can only control the inputs to get the outputs, that is called controllability. Here observability is nothing but only observe the internal nodes and output nodes, that is called observability. I will explain with the example. So here I am taking the combinational logic and these are the primary inputs and these are the primary outputs. Here I am taking the memory unit, that is flip-flop. So these are pseudo primary inputs and these are pseudo primary outputs. So these are the main inputs. To get the output, we can control these primary input, that is called controllability. And then coming to the observability, here observability is nothing but we can only check the functionality of the circuit. We can't able to control the circuit. We can observe the node, that is called observability. So here I will explain with the example. Here I am taking the circuit. E, F, G are the primary inputs and here 7 node is the primary output. 1, 2, 3 are 4, 5, 6 are the internal nodes of the circuit. For getting the 7 output, E, F, G are the main primary inputs. Here node 1, 2 and 3 controlled directly. So here 1, 2, 3 are controlled directly by using the primary inputs E, F. To trace node 7, so to trace node 7, 5, 6 nodes are used through these two F primary inputs. So this is for controllability. For getting the output 1, primary test vectors are 0, 1, 1. For getting output 0, primary test vectors are 1, 1, 1. So this shows that if node is very far from primary input, it is difficult to control. That is called controllability. Here observability is nothing but how functionality is going on in the circuit from starting node to ending nodes. Just we can observe the functionality of the circuit is called observability. And then coming to the fault models. Here simply we can say fault is nothing but it is an error or nothing but a mistake and also called as a malfunctions. It defined as the physical defect of one or more components is called fault. This can be divided into two types. In that first one is stuck at fault and stuck open or stuck short faults. These are done by the transistors. These stuck at faults can be classified into two types. That first one is stuck at 0 fault and second one is stuck at 1 fault. So stuck at 0 is nothing but a single line is stuck to 0 permanently. Stuck at 1 means a single line is stuck to 1 permanently. That is called stuck at 0 and stuck at 1 faults. So next fault models are stuck at faults, bridge faults, stuck open or stuck short faults. Okay, coming to the circuit. Here I am taking the NAND gate. This gate containing 2 inputs and 1 output. Here A is stuck at 1. So here stuck at 1 means this A input is always 1. If you want to assign 0 value internally to this A, it won't take the 0 value. Why? Because this A node is permanently stuck to 1. If it is stuck at 0, it won't take the 1 value. Why? Because it always stuck to 0. This is called stuck at 0 and stuck at 1 false. So I will explain with an AND gate. Here I am taking the AND gate. So forget about this stuck at 1. A, B are the inputs. For 2 inputs we can get 4 combinations. 2 power 2 equal to 4. So like that we'll get 4 combinations. Those are 0, 0, 0, 1, 1, 0, 1, 1. So output is for 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. Up to this correct output, fault free output. What about the Y faulty means? If B is stuck at 1. If B is stuck at 1 means this B is always stuck to 1 value. It won't take 0 value, right? So now apply the combinations. Now A0, B0. But here B stuck to 1. So that's why A0, B1. A0, B1. What is the output? 0. And then next combination A0, B1. Now A0, B1. Output is 0. And then A is 1. B is 0. It won't take the 0 value here because B is stuck to 1. So that's why now our input combination is 1, 1. For 1, 1, output will be 1. And then A1, B1. Again, we can get the output is 1. So according to this, instead of 0 value, we can get the 1 value. So this is the faulty output. Faulty output. At 1, 0 combination, we can get the faulty output. Same procedure for stuck at 0. Here B is stuck to 0. So that's why it won't allow the value 1. It's continuously taking the value B is 0. So at 1, 1 combination, we can get the faulty output. So this is about stuck at 0 and stuck at 1 false. I will explain the example problem. Here, how many fault-free sites are there? So total number of fault sites are 3. What are those? A, B, C. These 3 are the faulty sites. And then how many faulties are possibility? So total 6 faults are possibility are there. One is A0, A1, B0, B1, C0, C1. So these are the number of possibilities for faulties. So here I am taking the number of inputs A, B and combinations, and for this AND gate, this is the fault free output. If A stuck at 0, at 1, 1 combination, we will get the 0 instead of 1. At stuck at 1, 0, 1 combination, we can get 1 output instead of 0. At B stuck at 0, instead of 1, I will get 0 here. Like that, B stuck at 1, instead of 0, I will get 1 here. And then C stuck at 0, here I will get 0 instead of 1. So next, C stuck at 1, I will get 1 here as it is, and these 3 are the faulty outputs. So these red marks are indicates the faulty outputs in the circuit. And then coming to the bridge faults. So bridge fault is nothing but input to output short, input to input short, output to output short. So these 3 are the possibilities of the bridge fault. Here input to output path means input, if A is stuck at 0 or stuck at 1, automatically F also stuck at 0 and stuck at 1. So there is no need to extra path to take. Okay. And then if A is stuck at 0, B also stuck at 0. And like that, If F is stuck at 1, G also automatically stuck to 1 value. And this will cause improper masking or etching, and also loose or excess wires, defective printed PCB boards, and shorting of pins of chips. So this is the bridge fault circuit. I am taking here 3 inputs. For 3 inputs, you get the 8 combinations, and F is the output. Here I am taking the short path from A to B, so that is wide or wide AND gates. Okay, for 3 inputs you will get total 8 combinations. For 0 0, output will be 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0 0 1 0 1 0 1 1 0 0 triple 1 0. These are the fault-free outputs from this circuit. If it is wide or instead of 1 1, we will get the 0 0 output here. Wide AND gate, instead of 1 1, we will get the 0 0 here. And A dominant is only at 0 1 0 path, we can get the faulty output. Faulty output. This is about bridging fault. And then coming to the transistor faults. Transistor faults are 2 types, the stuck open or stuck short. So these two are done by the transistor paths. Means a single transistor is permanently stuck in the open state irrespective of its gate voltage. That is called stuck open fault. And stuck short fault means a single transistor is permanently shorted to irrespective of its gate voltage. That is called stuck short. I will explain with the example. So this is the circuit for stuck open fault model. Here I am taking the 2 input NOR gate, CMOS gate. Okay, here PMOS, and these two are the NMOS transistor. These two PMOS transistors are connected in series manner, and these two are connected in parallel manner. Here I am taking the inputs AB, and here taking the output C. So first I will give the inputs are 0 0. A0 B0 will get the output is 1. Okay, because of NOR gate. So this is the NOR gate symbol. A, B, C. If it is 0 0, 0 plus 0 0, due to this NOT gate it will get 1 output. Okay, if I apply 1 0, will get the output is 0. This 0 and this 1 is fault free outputs. Okay, for these two combinations, and these two are the outputs, and these two outputs are fault free outputs, and this circuit is fault free circuit, means there is no error or there is no fault in the circuit. If I am applying this transistor is stuck open, means we can get the output is Z. This Z determines the unpredictable output. So that means we can't say that value should be 0 or 1. So that stage is called unpredictable stage. Okay, so that is called stuck open fault. And then stuck short fault. So same diagram I am taking here. Here applying 1 0 combination to the AB inputs, I'll get the output is 0. Here I am applying the stuck short fault, means this PMOS is stuck short. Due to this, we'll get the X output. This X is also faulty circuit state. So if it is 0, good circuit state, means this is a fault free circuit. If it is X, means faulty circuit. If it is 0, that is fault-free circuit. This is about fault models. Thank you.